Welcome to Forum 360, the show with a local perspective but global outlook. I'm Sally Henning. Many people have heard of Einstein's theory of relativity, but did you know that some of the research that paved the way for Einstein's theory was conducted in Cleveland by 19th century professors Albert Michelson and Edward Morley? This is just part of the history and the legacy of Case Western Reserve University, which was previously Case Institute of Technology and Western Reserve University. Today, as part of that legacy, we learn more about Case Western Reserve University as we welcome two of its outstanding physics professors who are involved in world impact research and discovery. Our guests epitomize the theme of Forum 360, a global outlook with a local view. Professor Lydia Kisley and Professor Johanna Nagy, welcome to Forum 360. To let people know a little bit about you, Dr. Kisley is the Assistant Professor of Physics and Chemistry, the Warren Rupp Assistant Professor of Physics, a Forbes 30 Under 30, and a 2022 Allen Distinguished Investigator by Paul G. Allen Frontiers Group, a division of the Allen Institute, and she's known for building cutting-edge novel microscopes and other cool stuff. And Dr. Johanna Nagy joined the Case Western Reserve faculty just this July 1st, where amongst other research she does cosmic microwave background radiation experimental work. Dr. Nagy brings an international profile. Welcome to Forum 360.
Thank you.
Thank you. So let's talk about, first of all, what has been the most important reason why you went into physics?
So I guess I was lucky enough to become involved in research as an undergraduate student, and it was a wonderful opportunity. It convinced me that it was what I wanted to do. I kind of always knew I was interested in looking at outer space, and I loved the idea of being able to actually do things with my hands to build instruments that would answer these fundamental questions. So I got started out when I was young, and I just got hooked ever since.
Yeah, so why did I get into physics? I mean, I think it's a lot of fun exploring open-ended questions. I think that's what really attracted me to science, and being able to find something interesting, saying I don't know, and go at those questions for your job and the like. And I would say my route to getting to become a physicist was kind of a different route. Biology really interested me at first, and then taking chemistry courses and the way of using math and being quantitative about things attracted me more, about understanding biology, and then, I mean, getting more and more quantitative physics and the intersection of that with chemistry and biology is really how I ended up in the physics area.
Who were the people that influenced you, or the events that influenced you to go in this direction?
I'd say a lot of the teachers that I had in junior high, high school, elementary school, college, all of those people encouraging me and really making science interesting is, I think, I would say the people who influenced me the most in taking this route.
How about you?
I had a very similar experience, actually. So, you know, some great science teachers growing up in middle school, high school, some great mentors as an undergraduate and graduate school and beyond.
And what attracted you to Case Western Reserve University?
So I'm originally from around the Cleveland area, so I really wanted to end up back around here to be able to do both the science and be in a city I really like. And a great aspect of doing research here is I get to bring other people to Cleveland to do work in science in the area as well.
Well, that's exciting.
And I actually went to graduate school at Case Western, and so I was attracted to the graduate program in physics for just the great research that was going on there. And then when I got to come out and visit, I just saw how wonderful the department, the university were. So I experienced that as a graduate student, and then even though I have a different perspective now as a faculty member, I was really happy to be back because it felt like coming home. So I feel very lucky to be living in Northeast Ohio again.
So people think of professors as teaching and doing that as work, but I understand that you do more than just teaching. Could you describe that for our audience?
Yeah, so I think being a university professor, research is a really important component of our jobs. It's where we spend a lot of our time and for me at least, it was something that I was very passionate about that really made me want to do this job, so not just the teaching. And so for my research, I am a cosmologist. So I focus on trying to understand the universe just on its largest scales to try and understand how
A cosmologist is understanding the universe.
That's right.
The universe, not the university.
Yeah, the universe.
Yeah.
Yeah. So that's right. I try and understand the universe, just the big picture of how it got to be the way that we observe it is today and what it's made out of.
So are you involved in looking to see what the origin of the universe is?
Well, that's right. So I try and understand just the whole history of the universe. So what it was like when it was very young, when it was just beginning, all the way up to the present day.
Amazing. And you?
In terms of research or in terms of the teaching aspect?
The types of things that you do besides teaching and
Yeah.
types of research, yeah.
Yeah, because I would say your question was right on point. Many people say to me, like, oh, you teach, you probably have your summers off, but no. Summer right now, I have a lab of 10 people that are working in my research lab and managing that. And in terms of research, what I do is I want to understand materials at very small length scales. So to be able to do that, we need to build new tools to reach these small length scales. So
Now, when you say small length scales,
Yeah.
you're not talking about an inch. You're
No,
talking
I'm
about
talking
small.
yeah, I'm talking about nanometers. So
What is that?
yeah, so I would say like you can imagine, you can see the width of a single strand of hair. So if you divide that by thousands or tens of thousands or 10,000 or so, that's going to be down to the length scale that we're looking at. So you
you're
need to have
taking a hair and then dividing the hair into
yeah
tiny
fractions parts. That there's no way you'll
Less
be able
than-
to see that by eye. So we have to use cool things like lasers, really fancy cameras that are way better than the cameras on your cell phone or your iPhone.
Oh, I want one.
Yeah, yeah. So we have to build those instruments to be able to look at things at that scale. And we want to look at materials like, let's say, biomaterials, like if you're putting contact in your eye or getting a knee implant. You want to make sure that it's not going to get infected.
I usually prefer to have the doctors do that.
Yeah, but to understand what materials will work versus which ones won't work, we want to understand the fundamental physics of how molecules are interacting with that at these small length scales.
So you interact with the medical folks.
Yeah, so that's a great thing about Case Western Reserve is the
University
hospitals
hospitals.
that are around as well.
And Cleveland Clinic.
Yeah.
So tell us about your lab.
Yeah, so our lab, I guess I have 2 lab spaces, but the fun lab space where we're building these instruments is one in the basement, I guess across from where Joanna's lab will be. So the basement is the fact that like it's dark there because our cameras are very sensitive to light, and there's also less vibrations down there as well. And then we have very large tables that are a foot thick or a foot and a half thick.
The table is a foot thick.
Yeah, to reduce those vibrations, and they're also floated as well, so we reduce those vibrations. And then we have a lot of mirrors, lenses, so we can control where laser light is going, and then it goes through a microscope, and then we collect that light to be able to image these materials.
And you collect the light by?
With optics, so with a microscope, you have an objective that focuses the light. That's just a very fancy collection of lenses, so you can collect as much light as you possibly can and focus that light. So the same way that, again, your cell phone has very small, thin lenses to focus the light onto the camera chip in your phone. Things are out of focus or in focus, you want things in focus. So we have, instead of, I guess the lenses in your phone might be $1 or so. Our lenses are $14,000 to collect as much light as we can.
Ew, I shouldn't complain about the cost of my glasses.
Yeah.
Wow. Joanna, how about your lab? You said it's being built, or?
That's right. It's under construction right now, but I can tell you more about kind of the things we're going to do there and the things that we've done in sort of the labs I've had in the past. And so I think my lab actually looks maybe kind of different from what people might imagine a physics lab would look like. So in my lab, we actually build telescopes that look at microwave light. So this is not light that you can see with your eyes, but it's actually closer to the frequency that would be used for Wi-Fi signals or that a microwave oven would use to cook food.
You don't just open the door and look and there's the,
No.
you have to do more.
That's right. And so we're actually, in my lab, we're building all kinds of different components of these telescopes, and we test them before they get deployed to go observe the sky. And so parts of my lab look like they have very high-tech equipment and kind of, shiny stuff that people might picture. And then other parts look like maybe like someone's garage with just these workbenches with all kinds of power tools and little bits of leftover material and all kinds of stuff, because we do a lot of physical building.
There's been a lot in the news about the Chinese balloons, that where they were and what they were doing, going across the United States, where they're taking pictures. Are you getting involved with putting observatories on balloons?
That's right. So some of my telescopes actually, they do fly on balloons in the stratosphere. So they're up at about 120,000 feet or so. So we get above most of the atmosphere that would contaminate our signals.
Wow. And what are you looking for? What are you looking to measure? Microwaves, or what's the purpose of them?
Right. So we're trying to measure microwave light that comes from the early universe. So it turns out that this is the oldest light that we can see today in the universe, and it just happens to be in this microwave part of the electromagnetic spectrum. And so it's from when the universe was just a few 100,000 years old. Today it's about 14 billion years old. So it's very old. And we actually look at the polarization of this light. So it's a characteristic of light that you might be familiar with if you have a pair of polarized sunglasses. You can see it blocks out certain directions but not others. And so by measuring the signal, we can learn about what the universe was like when it was very young, and we can even learn about events that would have happened when the universe was much less than 1 second old.
So it's kind of a silly question, but just how far back can you look?
Yeah, so with the light itself, light when the universe was very young was continually being created and destroyed. So we can't really see any light from the early universe until it was a couple 100,000 years old. That's a lot less than 14 billion, but it doesn't quite go all the way back to the very beginning. But we can see other signals in the light that would have been imprinted by gravitational waves that would then interact with it later. And so that's how we can look back all the way to when it was just a second old.
So I'm glad to know I'm not as old as I thought. So what's been the most rewarding part of your job, Lydia?
Rewarding part? I would say my research group is still relatively young or new. I've been around at CASE for just over 4 years now. But I would say it's still been very rewarding working with students and seeing them develop from, okay, a student coming in, just being like, I don't know how to do any research, it sounds cool, being somewhat nervous sometimes, to being very independent, telling me stuff that I don't know, creating new knowledge. So that's been the most rewarding, is seeing the training of the students in the lab, going from me teaching them to them teaching me.
John, how about for you?
I would say something very similar, actually. I really love working with the students. And I think when a lot of people think about university students, they know they go to classes, but I think they don't realize that more advanced undergraduates and even graduate students will actually spend a lot of their time in the lab. So beyond your first year or two of graduate school, all of the school is actually just happening in the lab with these sort of one-on-one interactions with the other people in the group, and with all of your collaborators, basically. And so it's a really collaborative process, and there's a lot of just rewarding experiences in the teaching and learning.
Yeah,
My students teach me stuff all the time.
And I want to emphasize that the graduate students are in the lab, and a lot of people don't realize I don't really view them as students in terms of classes. They are the researchers. They're the ones that are doing the research, I would say even more so than the professor sometimes.
Yeah.
Because they have the dedicated time to be 100% focused on pushing the boundaries of science there, while we have some other responsibilities.
Well, speaking of rewarding circumstances, it's very rewarding to have our special guests today on Forum 360, Drs. Lydia Kisley and Johanna Nagy from Case Western Reserve University. I'm Sally Henning, and we're talking about their research today and their careers here at Case Western Reserve University in Cleveland, Ohio. So we talked about the most rewarding, what's been the most challenging? Just jump right in.
Yeah. Well, so for me, as we had mentioned a little bit earlier, I have these telescopes that fly on stratospheric balloons. And so there are all kinds of really fun instrumentation challenges that when you go from just taking something that works on the ground in the lab to actually making it work when it's up in the stratosphere, when it has to be nearly autonomous. We worry a lot about how much it weighs, about how it's going to work in different temperature ranges, and just doing all of the testing to make sure that once we launch, we're going to launch something that works, because it's really hard to fix once it gets up there.
Yeah, I would think. I have trouble changing a light bulb. Lydia, how about you?
Yeah, sorry if this is a repetitive answer that people sometimes say a lot, but like probably the pandemic has been the most challenging aspect of starting a new lab. We just moved in a couple months before the pandemic started, and being an experimentalist, trying to come up with things that people could work on remotely, or having people go into work where it was just one of them at a time instead of the team environment, I would say was the most challenging. But it's been, pandemics died down a bit, so it's great. It feels great when I go in the lab and everybody's around and interacting with one another, so it makes me appreciate that a lot more.
But it sounds like Joanna really has to work with remoteness.
Yeah, but most of the time we also appreciate being in the lab and being together most of the time.
And be able to share with each other.
That's right.
That intervention. What's been the most fun? Joanna, what's been the most fun?
Well, so I think for me, it's really fun when you've been working on a problem for a really long time, and then you can tell that you're finally making progress on it, and you see it work. And a lot of times this is because of the great students that I have in the lab. They're the ones putting in all the work. But when we've been working together on this problem, and then they come to me and they say, oh, I've solved it. I know how to do this now. And then they show me, and it's the best feeling. And that's even, it goes for some of the small problems too, just like all the little tiny things that go into making the big picture instruments work.
Oh, that's very, Lydia.
I'd say the most fun part of being a scientist that I find is meeting people from all over the world, getting to travel all over the world. Lots of people picture scientists of working alone or being stuck in one place. Like, we get to go to conferences all the time. I have collaborators.
That's just at airports.
Yeah, and having collaborators across the country and the world makes it a lot of fun. There's people I never would have imagined meeting when I was in high school in Cleveland, Ohio, and knowing people in Japan and Europe, South America, and stuff like that. Makes research fun.
Very exciting. What has been the most surprising thing that's happened? I'm going to start with Lydia this time, because that would be surprising.
Yeah, I would say surprising has been some of the research directions of, being at conferences, talking to new people, and coming up with a new idea that I never would have imagined my research would be going. So I have this project with a collaborator at the University of California, Santa Cruz, Laura Sanchez. And she's using a different type of method that instead of using light like we do in microscopes, they're measuring the mass of molecules.
The mass.
Yeah, the mass. So you don't have to put labels on them to make them glow or to be able to see them. You can measure many, many things at once. But it's a technique that I never ever thought about. But at a conference we met and we were talking, and I have a method where we stretch materials to make them bigger. And then that if you make things bigger, if your instrument has a set size it could measure, you can improve what you can resolve. So instead of measuring, let's say...
When you say resolve, you're talking about being able to see it.
Yeah.
Yes.
So let's say before you could measure a cell as a fundamental unit of life. Her technique before could maybe measure 10 or 100 cells. So you're averaging all of that information. But then with our method, if we can stretch and make that cell bigger, we could get information of one cell or even different areas of the cell. So it's a method I never would have thought of working with, but by talking and meeting at this conference, we're taking our ideas in new directions.
That must have a lot of medical implications.
Yeah, so that's our hope. We're demonstrating the technology now, but my collaborator works on ovarian cancer, and ovarian cancer nutrients and signals move from one area of the body to the ovaries, and understanding where those signals are requires you to track that over space and time. So her technique can resolve that. So after we demonstrate the technology, the goal is to then find out new information about where these signals that are telling cells to either be healthy or cancerous are going in tissues, and being able to resolve that.
Then you can also then see much more likely the impact of chemotherapy on the cells. You can have you.
Yeah, then we can also say not just, okay, what's the biology taking place? If we have some treatment, how does that treatment affect where those signals are going as well? Yeah.
Wow. Joanna.
Yeah, so I think maybe along a similar vein, I think for me, one of the most surprising things so far has just been seeing how much sort of our understanding of the universe and how much new stuff that we've learned has changed even just in the time, like since I've been a graduate student. And so I have particular instruments that I work on, but there are so many cool experiments out there, and there are so many different things that people in the community are doing. And these each have results that tell us something about a little piece of the universe. But when you start putting kind of all of them together and looking at the big picture, then there's some really powerful stuff that's going on. So, you know, even in just like the time since I started graduate school, I remember some of the things that we just didn't really know about the universe. Now we know, and we've seen them from multiple different experiments in multiple different ways. And so it's just seeing this progress where we get to piece things together. It's just really cool.
Well, China, what is, all of your work is significant, I'm sure, but as you view it, what is the most significant aspect of your work?
Yeah, I mean, I think for me so far, it's just this amazing idea that we can say anything about the universe when it was less than 1 second old. And so we keep looking for these signals from that time, and we haven't seen anything yet, but that still tells us a lot about what the universe must have been like, because we have some amazing theorists who can tell us in all kinds of different situations what we would expect to see in these scenarios. So even when we go out, if we don't see it, it actually tells us something about what the universe must have been like.
Lydia, what do you think? Most significant aspect of your work?
Most significant aspect, I would say, is that we can take a lot of tools that have been developed to look at biology and apply them to materials that engineers look at, and that we can do this interdisciplinary work and take ideas from one field and apply it to materials and these other medical or industrial problems. So I think that's the significance of my work. I'm not afraid to, I guess, put something new on our microscope to try to understand it at these new scales.
So what do you see as the global implications of what you're working on?
Yeah, so global implications, I have a project that's looking at corrosion, trying to understand that at new length scales or new time scales, or sensing that sooner. And then also some applications to separating molecules that are more energy efficient. So global implications, we're trying to select problems that have energy implications or safety implications and just try to understand the physics that's underlying them. So if we understand it on this fundamental scale, maybe we can impact those bigger applications.
Dr. Nagy.
Yeah, so
the global implications.
Right. So I guess part of what we're trying to do is actually using the universe as a laboratory to study this physics that we can't sort of recreate in our laboratories here on Earth. So we go out and we look at these processes, and I think it probes just a lot of really fundamental physics that impacts, just how we understand nature. And so I think a lot of this basic science just finds its way into all kinds of other places.
What's next for you, Dr. Nagy?
Well, so I guess with my research, there's always a progression of telescopes being built and looking at the data from telescopes that have already been observing the sky. And so I have a couple projects that I'm working on, both balloon-borne telescopes and telescopes that sit on the ground. And so I'm excited to see, once we get these out in the field and onto the sky, then what the data is that comes out of those.
Dr. Kissley, what's next for you, please?
Yeah, next for me, I've been talking a lot about cool microscopes or building tools. That's what we've been doing so far, but I think the next thing is going to be, okay, let's make an impact on those fields I was talking about. Let's make new discoveries about those materials, not just proof of concept, but then more application and talking to the engineers and material scientists to maybe even iteratively make better materials with what we understand with our methods.
So for the future, if I were to ask you what advice you might have for children who would like to go into the field of science and specifically into physics, maybe they like to build cool microscopes or maybe they like to play with balloons, what advice might you have for children?
So I would say keep asking questions and learn to get along well with others. And so I think, kids are always really curious. Yeah, play nice.
Play nice, yeah.
Yeah. So I think kids are always really curious, so the questions come naturally, and they just need to keep asking those questions because that's what scientists do. But I think also a lot of kids think that scientists just work alone by themselves in the laboratory, so they don't realize that when they're out playing sports with teammates or working on a project in school, that actually learning how to get along with all kinds of different people is really important for science.
Dr. Kissley, what advice might you have for children who might want to go into science, specifically physics?
Yeah, I would say realize that finding science to be a challenge or hard is a normal part of the process. That I find, they think that scientists find the math or the experiments, that it comes easy and naturally to them. No, science is hard and is a challenge. There's many times where you hit a brick wall and you think you're stuck. But if you learn how to overcome those challenges or persist through that, that's what scientists really do. Because a lot of time when I tell people that I'm a scientist, they're like, oh, those classes were so hard. It's like, those are the classes I found to be the most challenging and hardest. But that's why I found them interesting, that I wanted to try to still figure it out, even though those were the classes I had maybe some of my worst grades in, was in science. So that's the normal part.
And where did you go to school?
I did my undergraduate studies at Wittenberg University. It's in Southwest Ohio. It's a very small school, so less than 2,000 students, I think. It was smaller than my high school. So.
And Dr. Nagy?
I did my undergraduate at Stanford in California, and then my PhD at Case Western.
And where are you from originally?
I'm originally from California, actually.
Which city?
I grew up near Santa Barbara.
Ah, how beautiful. Well, on behalf of Forum 360, we want to thank our special guests. First of all, thank Case Western Reserve University for allowing us to interview them. Our special guests, Dr. Joanna Nagy and Dr. Lydia Kisley from Case Western Reserve University, where they are physics professors working on locally here in Ohio on scientific experiments, but working on things that have global implications. On behalf of Forum 360, I'm Sally Henning.
Forum 360 is brought to you by John S. and James L. Knight Foundation, the Akron Community Foundation, Hudson Community Television, the Rubber City Radio Group, Shaw Jewish Community Center of Akron, Blue Green, Electric Impulse Communications, and Forum 360 supporters.